Convolutional applied to types of data, text, signal data such as time series data, sensor data. It was specifically designed for this. The main core function or operator of the neural is the convolution, which was explained, where we convolve the image with a special function called a kernel. Those kernel weights are learned in the training process. And these CNNs has there's a class of deep neural networks. It's most commonly applied in analyzing visual data such as images and videos. And they are very particularly useful in capturing the spatial intelligence in the images. So they learn local features around the images where these kernels are scanning those images. And then these features are then learned at different levels, from low-level features such as edges, and then mid-level features such as shapes, and then finally it all combined together at high level to a definition of an object. And using those features, we identified what sort of objects are present in that image. Right? And we looked at one particular type of image use case in the last, and we applied some CNNs this use case. What is that particular computer vision problem that we looked at last week? So when you say there is an image, when you say well that there is a cat or dog or some sort of vehicles or some other objects. So what is that? It's called as, yeah, so it's a image classification. We already looked at it. How does the CNN process an image? It processes the image through series of layers. And there are different types of layers that are constructed to form this one single CNN network. And the different types of layers are convolutions, activation functions such as ReLU, and we have pooling functions such as max pooling, but there are also other types of pooling, but mostly max pooling is used. And after going through series of convolutional activation function and pooling layers, we finally end up with the fully connected layers, where this learned feature maps are then unrolled or flattened, and then we pass through another series of fully connected layers in order to classify the image into categories. So the image classification can be broadly classified into two types. One, you can call it as binary classification, where you say whether an object is present or not. It's just like a binary yes or no. But in most of the use cases, it will be a multi-class classification where we are trying to classify the image into one of the several classes that the model has been trained on. There is also another type of image classification called multi-label multi-class. So we have binary classification. We say whether there is an object is present or no. Then we have ImageNet or Cipher10, where we have, for example, in Cipher10, we have 10 image classes like aeroplane, bird, and some other different types of objects. And then when you pass one image through this network, it will classify that image into one of the 10 categories. Okay. So the output will be only one class. But there are also a type of neural network which can categorize this image into multiple classes within the same image. So suppose if you have car, bikes, and a cat and a dog. So it not only tells either one of them, but it can also say there are multiple objects present in this. So that is it's called multi-label. Then filters, we know they are also called as kernels, and they are applied on the image to extract features such as edges, textures, shapes, and other image description or sort of an feature maps that we learn from the images. And this process is called feature learning. And why do we use pooling layers in CNNs? Yeah, that's a good answer. So tooling reduce helps to reduce the dimensionality of the data so that we could have a much more efficient processing. And it does some dimensionality reductions and also tries to keep the most important features that has been learned in the previous years. So it helps reduce the computation and it also controls overfitting because if you have a large number of neurons, then the model tends to overfit. So we need to have a right balance between whether the model size is too small that it is underfitting to the data or it is too big and too deep. And if you are having a very simple data set and it might try to memorize everything and keep it into a very large neural network and it tends to overfit. So be careful in selecting the size and the depth of the neural network according to your data set and complexity of the data set. So we also looked at activation layers. There are many different types of activation layers, but the most commonly used is the ReLU. So ReLU basically makes all the negative values as zero and then keep all the other positive values as it is, just a linear transformation. But although it looked very simple, it was being found to introduce some nonlinear properties into the network, which helps to learn more complex patterns in the data. Because most of the data have some nonlinear nature in the data. And it is when you represent the data into a very high dimensional, hyperdimensional space, it is not easy to draw some linear separations between the data. So they are all very non-linear in nature. And this ReLU activation actually introduced some sort of non-linear properties to the network. And then we looked at some fundamental image processing concepts like thresholding. So thresholding, as the name says, we have a threshold and if the value of that image is more than a certain threshold, then we make it like white, and if it is less than the threshold, then we make it black. And this is particularly useful in the downstream image processing because your original image will be in RGB color image. Now you cannot do downstream image processing such as object detection or length measurement or area measurement or shape measurement directly on an RGB image. you need to first transfer the RGB image into a binary image, and all those white connected pixels forms your one single object, and then on those connected white pixels you can do length measurement, area measurement, or any shape analysis. So that is why this process of converting from a color image or a grayscale image into a black and white image, or it also called as binary image, is called thresholding. So this thresholding can be done in multiple ways. Very simple technique like applying a simple global value and make it more than those threshold, make it as white, and less than threshold, make it as black. But those simple techniques doesn't work always. So we have other advanced techniques such as adaptive thresholding. There are also some statistical based techniques such as also thresholding. Even in a way, edge detection is also doing a thresholding because it makes all the edges into white and remaining as a black. That's also certain types of thresholding. Then the very pragmatic or a practical concept in CNN is called transfer learning. So the transfer learning is a technique where we already have a trained model that has been trained on a very large data set. And this model has learned most of the informations based on like millions of images. Now, when we train on a custom data set, when there is two approaches. One is you can just start the training from scratch, but there is a much more smarter way to do it. That is, if you have a model that has already been trained on a very large data set, then you can reuse that knowledge because the knowledge of that model that has been trained on a different data set, but it's a huge data set. But all of the knowledge can be reused on your custom use case and custom data set, and that is called a transfer learning. And we looked at the techniques of how to apply transfer learning. Yes. Yes. Yeah. So if the images is not in the 10 minutes, like if it is a different use case and a different set of images that doesn't look like the data set or the images that has been already trained on. Yeah. Okay. So any questions before we move into today's topic?
Hello.
Hello? Yeah. Yes.
Yeah, I'm audible, sir.
Yeah, audible, but it's only coming in my computer speaker. Not sure
Okay.
why. Okay. Go ahead with your question.
Yeah, so the one small question in the PPT of day one, if you look at it, I'll just tell you the page number.
Oh, 1 second, your volume is little low.
Yeah, is it better now?
Okay.
Yeah, is it better now? Can
Yeah,
can you
it's
hear?
better now. Yeah.
Okay. So just referring to the slide number 6 of day one.
Okay. 1 second.
Yeah,
Hmm. Is this the one you are referring to?
filtering, yes, sir.
Yeah.
So
Tell
my
me.
my question was how are you making this kernel 3 by 3 matrix? What is the logic in this one, sir?
So these are all kernels designed by some mathematicians and computer scientists um, way back some 40, 50 years back by, say, a scientist called Sobel, another guy called Canny. They all designed this. And this is based on differential equations and differential calculus.
Okay.
So what they do, if you look at the image, there are all different levels of gray. And when you move from a black to white, there is a step gradient effect, right? So there's a change in the gradient. Um, so if you, let's say, take those image data as one single volume of data and you try to apply some differential equations, like dy by dx, it basically calculates the change in the intensity of the pixels, and that we call it as gradients. Now you have to have a special mechanism in order to calculate this gradients over a matrix, and you also need to come up with a very compute efficient way. It's not like a simple one-dimensional vector where you can just go through some sort of an for loop, and then you just calculate the current value with the previous value and the next value, and then you cannot do that. Then you just take like hours to calculate those gradients. And that basically those mathematical differential equations is then converted into these kernels, and then we convert those images with these kernels, and the values that's gone into these kernels are mathematically been driven or derived, sorry, by mathematicians like Sobel and Kenny, and then that is how they designed these kernels. So there are papers very old. I mean, I don't know if people still read it. It's like 40, 50 years back they have invented this. Okay. And
Yeah.
even let's say even if you take a median filter, right? So what
Mhm.
it does is um, it takes a 3 by 3 pixel of an image, okay, and
Yeah.
those 3 by 3 totally 9 values are there, and those 9 values can range from 0 to 255. And what does
Yes.
median does is it takes those 9 values and then short it down from small to the biggest and take the median value and put it into the output image.
Yeah.
Okay, that's a
Yeah.
simple, very
So,
basic median filter. Same you can say with the average filter, which means it takes the 9 values and then average it out and just put that average value in the output.
mhm.
Similarly, for Sobel, you have this kernel, and this is basically the original image pixel values. And what we are
Right.
doing is we are doing element-wise multiplication, right? So we are
Right. Right.
multiplying 2 with
Mm.
1, 3 with 0, 1 with -1, and so on. And then finally we are adding them, and then the 3 will be the output pixel values.
Yes.
Okay.
Yeah.
Now, this type of filtering is sort of being replaced with the deep learning kernels. Now, as I told you earlier, the mathematicians and research scientists used to design this kernel, and there will be like one paper just explaining how they came up with the kernel. And then there is like multiple kernels you need to hand select by yourself. You should know what filters is applied for what purpose. Okay, there will be like 10, 20, or even more filters. But nowadays what happens is we have moved away from that to a convolutional neural network, where we still have that the same concept where a kernel is still applied on the image, but you don't have to design these kernels on by yourself. The model learns these kernels on its own. All you need to just to give the data. Based on the
Mhm.
data, it learns what are the values of these kernels so that I can do the task that has this neural network has been designed to do. For example, if it's image classification, the task of the neural network is to classify that image into one of the categories. So initially it makes mistakes, it just makes some random guesses, but then we calculate the loss, we then just do back propagation and update these kernels iteratively over 100 epochs or 300 epochs until the loss is reduced, and then finally we'll have a kernel that can extract all these important features from these images. So we have moved away from this probably
Okay.
long back to this kind of automatic learning of kernels.
Okay, sir. Understood. Thanks.
Okay, thank you.
Yeah.
Yes. Yeah. So these are the model parameters or weights that is learned in the learning process. Okay, if there are no more questions on last week, so let's move to today's or this week's session. So this week we'll be looking at
one
yeah.
question, sir. So in the previous one, the receptive layer, input layer, you told that particular number of pixel it points and feature map happens. So there is a multiple layer in CNN also, right? In the multiple layer, the receptive, wherever your input selection, it remains constant or it changes for one particular feature map. Suppose some corner pixel you are taking for different layers, it remains same region of pixel or it changes.
So the receptive region is basically determined by the size of these kernels. So now it looks at 3 cross 3 pixels, but it is mostly they use 3 cross 3, but in some of the CNN neural networks, they sometimes use 5 cross 5, or they may even sometimes use 7 cross 7.
So
Okay.
my question is a little bit different. So there is a mapping. You see that 3 cross 3 to feature matrix, there is a mapping. This mapping for over multiple layers remains same or it changes? That is my question.
What do you
Did you?
mean by mapping of from where to where? So we are in an image and then we are convolving with the kernel, and then we land up in a intermediate feature map, and that will have a reduced dimension mostly from the input dimension. Okay. Probably let's say if we have a 7 cross 7 input dimension, if we convolve it with some 3 cross 3 kernel, it then reduces to 5 cross 5. And then again, from 5 cross 5, it might reduce further to 3 cross 3 and so on. Now, what you are asking is whether the mapping of 7 cross 7 dimension to 5 cross 5 remains the same from 5 cross 5 to further dimension reduction like 3 cross
Yeah.
3.
Yes.
Uh, the extracted dimension gets sort of compressed in every layer.
Yeah.
So you have a lot of features at the initial layers, but then these features are then combined together to form some connected regions or connected edges like that. So they are not directly mapped one-on-one, but they somehow tries to combine all the informations into a lower dimensional space. So it's more
Okay, they
like
try to.
PC.
Okay.
Yeah. Yeah. So if
Yeah,
you
got it.
know PCA rate, if let's say if you have starting with uh, a very large dimension of, let's say, 1,000 plus dimension, but finally you ended up with some three principal components. So what it does is it tries to find three vectors that is representative enough of those high dimensional space. So each of those principal components represents those high dimensional space in a specific way. So similar kind of dimensionality compression and image compression is happening here. Yeah, I'm not sure if I answered. Yeah. It's a little bit abstract concept. It's very difficult to explain what is going on, but you could actually play with that CNN visualizer to understand what is going on.
Okay.
Okay. But it's
yeah, that one.
Yeah, but it's a very good question. Yeah.
Thank you. Thanks.
Let's start. What is the difference between movie versus the art of value grade? Like max pooling.
Yeah.
What is the difference
Between a convolutional feature extraction and the max pooling, right? So the max pooling actually reduces the dimension by half, and there is quite a bit of information is lost. So probably only half of the information is kept. Okay. So mathematically, it's very simple. It just takes max value for every window. There is the most of the feature extraction is happening in the convolutional layer. Okay, which means all those your important features such as edges, the shapes, and all is extracted by the convolution layer only. Max pooling layer does not doing anything. It's just compressing. Okay, but it's similar to again like a PC only, but it compresses in such a way that it maintains the most important features. But it is surprisingly powerful that how can just taking a max value will keep the most features and then also reducing it. That is why it is very difficult to explain why this works. It's more like an abstract concept. Probably there are certain blogs or papers which explain this in detail. But looking intuitively, there is nothing that max pooling does other than that reducing the dimension and then avoiding like overfitting by reducing the total number of neurons. It's completely different. If you ask what is the difference between feature mapping and max pooling, most of the information is extracted by the convolutional layer. Max pooling just does a dimensionality reduction.
Sorry, Doctor, is it Doctor?
Okay, so I was telling like what would be our today's agenda. So today we'll be looking at one of the important problem called detection problem. So last week we looked at the image classification problem. So this week we look at object detection problem. And this would be the one of the most industrial application computer vision a problem that the industry would be applying. The extension of this or a more advanced version of the object detection would be the image segmentation, and that we will look at next week. So we look at the fundamental concepts of object detection. Then we will see some basic concepts like what are the different evaluation metrics that are used in object detection. Then we will look at the modern taxonomy of object detection architectures or frameworks. because the object detection has evolved a lot over the last 10 years. We look at them, and then we will then see the YOLO framework and how the YOLO framework itself has evolved over the last a decade. And then we'll see what's the latest advancements in the object detection, such as the transformer-based object detections. You might have already heard about transformers. Then finally, we will look at some practical tips and considerations, how we can implement these object detections effectively. Okay, so I have divided in today's session into 4 parts. The first part will look at object detection fundamentals. These concepts are model agnostics, which means that they are common to all different types of object detection frameworks and architectures. So they can apply to the old generation object detections. They apply to the YOLO series, which is more widely used. They are also applied to the latest advancements, such as the transformer-based detection models and the production systems that you might be building. Okay. So object detection is another type of computer vision technique or a use case that works to identify and locate objects within an image or video. So if you compare this with our last week computer vision technique image classifications, the image classification as pointed out in the left-hand image, it just tells there is one label for the whole image. For example, it will tell whether there is a cat in this image or not. But the limitation of the image classification is that we cannot, it will not be able to tell the location of the object in this image. So we cannot tell where the cat is. Okay, there can be one cat or multiple cats in the image, or there can be multiple objects, both cat, dogs, and other types of objects in the image. But with just image classification, we cannot solve some of the practical problems. So take, for example, self-driving cars. Is it enough to just tell there is pedestrians, there are trees, there are cars? So it is not enough, right? We cannot just build a self-driving car just with an image classification. What information is required is to not only just say what object is present, but tell me where these objects are. I need a precise location, whether they are in left side of me or right side of me or front of me or back side of me. Then only I will have a spatial awareness of the different types of object present and where they are present, how close proximity they are present. Then I would able to then take further actions based on all this information that are collected at the using this visual intelligence, right? Same for the video surveillance. We want to, for example, take vehicle surveillance or vehicle monitoring. We also want to know where these cores are present, and we also want to identify the cars and also tell how many cars are present. We just don't want to say, yeah, we have cars in this image, but also tell or count the number of cars. In order to count the number of cars, then we need to locate those cars and then draw some sort of a bounding box around those cars and count them. And then defect detections in industrial inspections. We don't want to tell whether there is a this image is defective or not, but also locate that defect within that image. For example, if there is a crack, okay, tell me where that crack is. So for that, I cannot use image classification models for these types of problems. I need a different approach, and that is basically what object detection does. So what we do is we move from classification to localization plus detections. So in the middle, we say that, okay, there is a cat, but I also give you an additional information about the location of the cat. And in the right, we say that, hey, there are different types of images or objects are present in this image. I give you the location of these objects, but also I will tell you what these objects are. So the blue box represents the dog, the green one represents the person, and the right one tells you where the cat is. So how does object detection works? All machine learning, all deep learning, there is always good to understand as an input-output mapping, right? So you give some input and the model, it's passed through the model and the model outputs something. In your image classification, your input is an image, a 2D image, and the output of the image classification model is one of the classes that the model has been trained on. If it is a cat versus dog image classification, it will tell you whether it's a cat or a dog. Now for object detection, how does this output differs from the image classification, right? In the previous slide, we saw that it does not only tells you the class, but it also tells you the location of those objects. In order to give the location of the objects, what we need is called a bounding box. So in object detection model, it takes image as input and then it outputs a finite subset of possible bounding boxes and an image. So in this previous example, if I give this image as an input, it will output 3 bounding boxes. And each bounding boxes will have 2 things. One, the coordinates of the bounding boxes. We'll see how a bounding boxes is represented in upcoming slides. 2, it will tell you what object that bounding box is associated with. So it will output 3 bounding boxes and it will tell you the coordinates of this bounding box, and it will tell you this blue box is associated with dog, and it will output the coordinates of this green box and it will tell it is associated with person, and the red box will have its own coordinates and it will be associated with cat. So in this case, it is just 3, but it can be more than 3. So there is an sort of a finite number of bounding boxes that it can output. Typically in modern object detection networks, they limit this into probably 100. So they can detect 100 objects per image. In theory, it can do infinite because there is no any limitations as long as it can draw bounding boxes in the images. It can do actually infinite number of bounding boxes. But in modern object detections, what it does is if you pass an image into an object detection, it will come up with some, let's say 20,000 possible bounding boxes in the image. Then what happens is it then goes through a series of post-processing, which we will look into it in a short while. Then out of those 18-20,000 possible bounding boxes, we filter them and eliminate the unwanted ones. And max to max, we can have, let's say 100 bounding boxes in an image. It's a typical, but it might differ based on the framework. So I already explained each detection has a bounding box with its class label, and there is also something called as confidence score. So you already know in image classification also, in the final output classification layer, for every class, it outputs a probability score, right? In this case, it is the same. Instead of calling it as probability score, they call it as confidence score, which indicates how confident that model when it says that that bounding box is of a particular class. Okay. So in this example, when it outputs these three bounding boxes and its class, it will also output what is the confidence score. So the blue box can come up with the confidence score of 90. The green box can come up with a confidence score of 70. The red box can come up with a confidence score of, let's say, 80. So each will have its own confidence score. Okay. Now, in real, when the model process these images, as I told you, they have output like a lot of bounding boxes. One way to filter the unwanted bounding boxes to filter them with the confidence score. So we will retain the bounding boxes only if the confidence score is more than a certain value. Typically, they are 50% and above, right? So the model can output the bounding boxes with confidence score anywhere between 0 to 100. But we will say, hey, remove or filter out all the bounding boxes which are of no confidence score. So whichever is less than 50%, we just simply eliminate them. But that is a general guidance of keeping the bounding box with the confidence score of 15 and above. But in reality, we select this confidence score based on a certain evaluation or criteria. So that also we will look at it a little later. So we evaluate the model, we'll see how the model performance at different confidence levels. And then we select an optimal confidence score where the model has a balanced performance of detecting the objects, but also not detecting too much that most of them are wrong predictions. Okay. Okay. I think we covered the basics here.
Question before you go to the other one.
Okay.
Yeah. So can you go back to slide number 4?
Okay.
Yeah. So just referring to the picture number 3, if you go to the next slide, you have details about. So this will be like typical output, like you have a class. So here will be there will be two more things, right? Class will be human or whatever dog, right? It will come with the confidence score.
Yeah.
When okay, so now you said that in the modern thing, right? You have 20,000 possible boundary box or classification. For image. If you give a input as an image, there are 20,000 possibility, right? Possible. So what are those classes, sir? Can I have some details on the classes? Like for example, in this case we have 3, right? And per image there could be um, you said 100 boundary boxes or classification, right? So similarly, the other one in the modern, I think modern way we are handling is 20,000 boundary boxes or classification, right? So what are those classification? Can you just give some idea?
Yeah, I understood your question. So basically, object detection, they are trained on a data set called MS COCO dataset. So it's from Microsoft. COCO means common objects in context. So this MS COCO dataset, they have like lakhs or millions of images. and it has 80 different classes. You can see here, right?
Right.
80 objects. So these are some of those objects like airplane, cat, dog, fire,
Yes,
boat,
got
like
it.
that. So this is what the most of your pre-trained models, the open source pre-trained models, they are trained on this data set.
Okay. All right. Thanks, sir.
So now we look at a very simple concept because bounding box is a fundamental structure, data structure of object detection framework. Now we need to have some basic understanding. It's very simple and straightforward. A bounding box is represented by coordinates, and these coordinates they have a different formats. And some of the common formats is basically XY, which means they are represented by the top left corner of the bounding box and the bottom right corner of the bounding box. So the top left is x1 comma y1, and the bottom right is x2 comma y2. And if we know the top left and bottom right, we can calculate the height and width of the bounding box. The height and the width of the bounding box is required in order to calculate the area of the bounding box, and that area is actually useful in the downstream calculations, such as calculating a metric called intersection over union, which we will see it in the next slide. Okay. Now, what is important to note here is there is no any universal way of using one format in every data set or every model architectures. There's a slight variation in these formats. So just be aware of these different formats that are commonly used in object detections. The most one I already explained is represented by x1 comma y1, x2 comma y2, which is the top left and the bottom right. Sometimes they are also represented with just the top left, and then instead of giving the bottom right, they give the height and width of the bounding boxes. Now, if we have four of them, right? If we have just xy, height and width, you can automatically calculate x2 comma y2, right? So x1 plus width is nothing but x2, y1 plus height is nothing but y2. Okay. There is another format called CXCYWH. So instead of, let me take my pen. So instead of giving the top left and the bottom right, what they give is the center. So this they call it XC, comma YC. So if we have XC, comma YC and the height and width, you can calculate x1, y1. Also, you can calculate x2, y2, right? Which is nothing but xc minus width divided by 2, right? Then you will reach here. This is basically what is that. Then if you know yc, then if you subtract half of the height, then you will reach here. The same way, if you add the half width to xc, then you will get x2. And if you add half of the height to yc, then you will get y2. So these are the different formats and that you should be aware of. Sometimes if you don't pay attention to this of what format is being used, and if you are confusing or mixing up things, then your model training or evaluation or during inference, you might not get the output that you are expecting. Then if you're trying to debug and if you're not paying attention to these formats, then you might be getting confused on why I'm getting different outputs than what is expected. Okay, these are small things just need to take care. And most of the nowadays object detection frameworks are based on YOLO format. Um, so they use this format of putting the class first. So if you have a label of if you look at the label data set of an YOLO data set, first they will have the label, or they might even have a label index instead of the label itself, which means they will have some sort of a number called 1. So 1 represent cat. And then what they will have is a normalized coordinates of the center x comma y, and then the width height. What do you mean by normalized coordinates? Which means they are not anymore into the pixel coordinates, right? So pixel coordinates starts from this is, let's say it's 100 comma 100 image. So this is the outer box is an image. So this image is of the dimension 100 comma 100. Okay. Now not all images is of the same dimension. Some will be 100 comma 100, some can be 200 comma 200, some can be 300 comma 400, right? Now in order to keep the bounding box agnostic uh, from these image sizes, varying image sizes, we can normalize them, right? So we can say take xc and divide the by the image width. So, and then the same take yc and then normalize it by the image height. Then you will have xc, yz not anymore in 0 to 100. You will have it in the range of 0 to 1. Okay. Then what you can do when you want to again move back to the image pixel coordinates, you can then take the normalized x coordinate and multiply that with the image width, then you will be back into image coordinates. The same take yc and multiply it with height, then you'll be back into the image coordinates. So usually the models are trained with normalized coordinates, and that is what the model also will predict. When you run an image through this YOLO object detection, it will give the bounding boxes in normalized coordinates only. It will be between 0 and 1. But if you take that coordinates and then if you're drawing it on the original image, your bounding box will not be aligned with your object. Then you will realize that you have not done the denormalization, right? If you are not transferred back to the image coordinate. So you have to do this multiplication so that your bounding boxes will be aligned with your image coordinates. Any questions here? These are like simple maths. Do we do image resizing also? Yeah, that's a good question. So when we train these models, they are not trained typically on the original image sizes. An original image size could be, let's say, 1280 cross 760, some sort of HD resolution. If you look at the YOLO object detection models, they are typically trained on image sizes of 640 cross 640 or 410 cross 410. Okay, so you resize them. So you also should know that, okay, I need to go from 640 cross 640 back to 1280 cross 960, which means that during the model training, it is already normalized to 0 to 1. If you have your bounding box coordinates in normalized coordinates, you can go from there to 640 cross 640 or 1280 cross 960. So that is a simple multiplication you can do. Yes, yeah. So typically, all those pre-trained models that are available in the open source in the GitHubs, they are trained on 640 cross 640 because of the uh, because if you're training it on the full size image, it takes a lot of time. And if you're training it for millions of images, it may take months and months to train. So you need to first evaluate, do we really need to train it on the full resolution image? That depends on the use case. If your target object sizes are very tiny, very small, I think it is advisable to train on the full resolution image. And again, this is also very experimental. It is advisable, but it is not always guaranteed that if you train on full resolution image, you might get 10x improvement. It's not like that. You might get some 2% to let's say 5% improvement, and that 2% to 5% improvement may be significant for your use case. So sometimes people say, okay, let's go with full resolution image training. Okay, so the practical tip here is start with smaller size, let's say 640 cross 640, keeping in mind that, hey, when I reduce the image size, I am actually losing a certain information. I need to first go through a first iteration of model training and then evaluate my model performance on field testing. And during your field testing, you realize that, hey, I'm missing a lot of tiny objects. My model is not detecting tiny objects of below a certain size. Then you can attribute that problem to, hey, that might be because that I have reduced my original image into a lower sizes, and because of that there is a loss in information, and that's why my model is not able to cope up with these tiny objects. Then you train a model with the full resolution image. Then you compare the performance. Then if you see some good improvement, then probably training it on full resolution is what is needed. Okay, that is one thing. Another thing, it also depends on your deployment architecture, like what kind of compute power you have in your device, right? If you are limited with the available compute, it is not always possible to run inference on the full image size. Let's say running inference on 640 for 640 takes half a second. Running the inference on the full size will take 3 to 4 seconds. So it will be like 4 to 5 times slower than what you can infer on the small size. But if you don't see big performance boost between low resolution image and high resolution image, you will obviously choose low resolution image so that you get a much faster inference than running it on full image. Hmm. Hmm.
So it will also depend on the type of application.
Hmm.
So it will also depend on, let's say, the kind of camera which I'm deploying,
Hmm.
which is capturing the image.
Yeah.
See the camera which is capturing the image, capturing image. So, first the camera, second, within that, what I call the system altogether. I am what kind of application I'm putting across so that I'm putting resizing the attention and then processing all that data in real time. Do you think that how do we actually do that? But then in the real case scenario, you miss out.
Yeah, so in self-driving cars, they might have a full supercomputer embedded within the car itself, let's say, right? They might have designed in such a way they have enough computing power in it. And then if in self-driving car, most of the objects are of sufficiently large. So they are detecting cars, pedestrians, trees, and things. So mostly for self-driving cars, uh, uh, reducing the size might not lose those information, or they are not landing up in a problem that they are not able to detect micro objects. Okay, so they can do this down scaling. But in industrial applications, there are some very tiny defects that needs to be detected. Even in medical applications, right? They have very high resolution image because they have to identify very tiny cells. That is in medical, there is no any time limit, right? You can just investigate one image for an hour or so. So depends on the use case to use case. Yeah. Mm-hmm. How to?
Identify expert access.
So this is an image, right? You understand this. So the outer bounding box is an image, and the inner one is basically a bounding box. And you know, right? The image dimension is of like this typical. So this is what HD image dimension is. It has 1280 uh, width. This is basically the width, and this is basically the height. So basically what I'm saying is I have 1280 columns like this, and I'll come to that. So basically this image, right? So they are nothing but pixels, matrix like this, right? So each pixel has a coordinate called x comma y. Okay, this is x. The vertical is x, and then this direction is called y. Yeah, but x is basically the rows. Okay, and y is basically the columns. Yeah, in a typical graph, you just plot x here and this, but in image, it's the opposite way. So x represents among this, where am I? Am I at 0 or am I at 960? Okay, and then y tells among this vertical partitions, am I at 0 or am I at 1280? Okay, so in this, what will be my center? Can you tell me? Yeah, so 960 by 2, you understand, right? You follow me, right? So this is basically the center, 1280 by 2. So that's how the coordinates works in the images. Now, if you have, let's say, one object like this, let's say call it this as an apple, and then I'm drawing one bounding box around it. Okay, so this bounding box is represented by two coordinates, x1 comma y1, which is my top left, then x2, sorry, x2 comma y2. Okay, which means just approximately this x will be somewhere like 1000, because this is 1280, right? So if I move from 0 comma 0 all the way up, this is my x, so it will be around roughly 1000. This y, it will be somewhere in 10, because this is 0 comma 0. If I move a little bit, this will be my 10. Understand, right? So that is basically the coordinate system of images. So now what is your question? The model will identify. That is what the model is trained to output. So similarly, how we have this series of convolutional layers, max pooling, and all those things. The object detection architecture is different. It will also have series of neural network layers. In image classification, it is trained to output just one vector like this. Okay. So let's say it is 4 model classification. It will tell you first class is 95, second is 0.01, something like that. That is what it will output. Then you say, hey, this is my highest probability. So then this image is cat. That's all it will output. Okay. But object detection, it will output 3 things. It will output bounding boxes. So it will output a series of bounding boxes. And for each bounding boxes, it will tell you what is the class, what is the confidence score. That will be its output. That's why we defined what will be the output of an object detection. It's kind of followed me. Okay, but I'm not sure if you are also asking about how do we create these bounding boxes in order to train the model. Then that is basically the labeling process. So first you will collect images, and that images will contain all those target objects that you want to identify. Then the first task is to go and label them. So you go open one image by one image, and then you manually draw a bounding box around it. And that bounding box is what is the input data to train your object detection model. Okay, there are tools to label these images and draw bounding boxes around them. So one of the tool is called CVAT. Okay, so I'll just quickly jump there as well. So you can open or search for CVAT. So this is an online tool. They also have an on-prem version or a local deployable version of it. But we will use the web version of this event for today. You sign in using your Gmail. Okay, so CVAT is basically a complete data labeling suite for the computer vision use cases. It's an open source. This was originally built by Intel and has been open sourced. Now they have two things. One is completely open source version that you can install locally. Another is an online version where you can have some free account and use it. But there are some advanced features that are part of this online tool that you can get access to it if you have a paid or licensed subscription to it. So basically it starts with some project, right? Let's say call it demo project. So here you need to configure what type of objects you want to identify. Okay, so now let's call it car. Then we can call it pass. Then we call person. Okay. So now it created a project. Now what happens? Yeah, so here I have my project. In this project, I have three types of objects. Now this next is to import some images. So let's see. Probably first we need to create a demo task. So here's where we need to upload images, maybe for demo purpose, I will do I have some example images. Let's open this image. I have uploaded just one image. Okay. Okay. So in this is basically a labeling. So I start by labeling them. Okay. So this is one bounding box. Another bounding box I can draw like this. I can then keep on drawing. So this is what the model will be trained on. So now I also have a person box, right? So I can just label them. Okay. So I have four bounding boxes. Each of it has XY coordinates and it also has its class label. So you can then export them. So for example, we export them into YOLO format.
So, sir, one question on this one. So this
Uh-huh.
will be normalized, that pixel will be, when you are exporting, this
Uh-huh.
image pixel will get normalized here, or it will be not normalized?
Yeah, it depends on the format. I think for YOLO it gets normalized. We look at that file here.
And also, if you want to select like multiple files, and because it is a time taking job, right? We cannot do one by one image, right? So
Okay.
how do you do that? For example, if I have 5 images, you do it in once and it gets reflected?
No, you have to do one by one, but for
Okay.
video, you might have repeated frames.
Okay.
For that, we use some advanced annotation techniques like trackers, which means
Mm.
if you label in the first frame, these labels are
Mm.
then copied automatically to the subsequent
Second.
frames. Yeah, so
Okay.
that makes a little bit semi-automated.
Right.
But those trackers are not always perfect. So at least it copies and it has a starting point, and then you review and then you adjust those bounding box if they are not correct. There are little bit semi-automated ways available in this tool.
Okay. Thanks.
Sorry? Yeah, for videos, right? Because for videos, it's also moving objects. So if you label a car, then it is also present in the subsequent frames. If it is not moving, it will be in the same pixel location. But if it is moving, it does a little bit of tracking. If it is a linear movement, it will work good. But if it is moving like this, then it loses tracks. Huh? Uh-huh. Yeah. Yeah. Yes. So now let's quickly look at that exported format. Then you'll get an idea of how this box looks like. Annotation is that yeah, 1 second. So this is how the bounding box labels will be.
For the first.
Yeah, if you are, for example, training an object detection for your custom use case or your own project, you need to first start with CVAT. First, you need to collect images. Then you need to create a project in CVAT, and then go and label them, and then export them. And this is how the label will look like. So here you can see they are all normalized coordinates. Yeah, this is XC, YC, WH. So this is in the YOLO format, this format. Yeah, CH, CY, WH. Okay, so you can also export it into different formats. For example, if your pre-trained model is not in YOLO, and if there is some other thing, and they are trained it on other formats such as Pascal, VOC, or MS Coco, only 3 major formats are there: Pascal, VOC, MS Coco, and YOLO. Okay, so they have a little different format. If it's the same thing, if I export it into Pascal VOC, it basically gives you an XML file instead of text file. So then it will have a little bit XML structure of the data. Then you need to know how to understand that XML structure. It's very pretty simple. Okay. Okay. Should we take a break? No? Okay. Okay, let's have a break and then come back and continue. Thank you.